There are two very different ways a shape can repeat forever. The first is familiar. You take a shape, slide copies across the floor, and cover the plane. Squares do it. Equilateral triangles do it. Regular hexagons do it. In fact, those are the only regular polygons that work. Why? Because around every point the angles have to add to exactly 360 degrees. Triangles contribute 60 degrees, squares contribute 90, hexagons contribute 120. So 6 triangles fit, 4 squares fit, 3 hexagons fit. But try regular pentagons. That angle is 108 degrees, and 360 divided by 108 is not an integer. Eventually you get a gap, or an overlap. So regular tilings are rare, but irregular tilings are almost too easy. Any triangle can tile the plane, any quadrilateral can too. Take a random 4-sided shape, make a copy, rotate it 180 degrees. Its opposite sides line up automatically. Repeat that pattern forever and the plane fills. So the interesting question is not, can a shape tile the plane? The interesting question is, can a shape tile itself? Can one large shape be cut into several smaller copies of the exact same shape? That is called a reptile. A shape is rep k if it can be divided into k smaller pieces, all congruent to each other, all similar to the original. And the number k is not just a label, it controls the geometry. Suppose a shape is rep 4. Its area has been split into 4 equal pieces, so each small copy has 1/4 the area. That means its side length must be scaled by 1/2, because area scales as length squared. This is why every triangle is rep 4. Draw the 3 mid-segments, lines connecting the midpoints of its sides. You get 4 smaller triangles. Each has half the side length, each has 1/4 the area, and each is exactly the same shape as the original. Now reverse it. 4 tiny triangles make 1 bigger triangle, 4 bigger triangles make an even bigger triangle, then 4 of those. At every zoom level, the same triangle returns. That is not ordinary tiling. Ordinary tiling repeats through space. Rep tiling repeats through scale. And this is where it gets weird. If a shape is rep 4, it is automatically rep 16, because each of those 4 smaller copies can itself split into 4. 4 times 4 gives 16, then 64, then 256. A single rule compounds forever. But not every reptile has a nice whole number scale factor. Consider a rectangle with side lengths 1 and square root of 2. Cut it in half. Each half is a 1/1 over square root of 2 rectangle. Rotate that smaller rectangle. Its proportions are still 1 to square root of 2, so each half is a scaled down copy of the original. That rectangle is rep 2. Its scale factor is not 1/2, it is 1 over square root of 2. And that has to be true. If 2 copies make the original, each copy has half the area, so each length shrinks by the square root of 1/2. This is the hidden rule behind every reptile. If a shape is rep k, its linear scale factor must be 1 over square root of k. That simple equation tells you why square numbers are special. For rep 4, the scale factor is 1/2. For rep 9, it is 1/3. For rep 16, 1/4. These are easy to build on grids, but for rep 2, rep 3, or rep 5, the scale factor involves square roots. The pieces have to fit with much more delicate geometry, so a reptile is more than a tiled shape. It is a shape with a recursive blueprint built into it. A shape that can be cut into copies of itself, copies that can be cut into more copies. And if you zoom out forever, the same geometry keeps coming back. That is one of the strangest things in mathematics. A finite shape can contain instructions for an infinite pattern.